Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. So here we can use these thin films to observe the boiling process. And the heat source is going to be our soldering iron. And the films will be a little bit thicker in this case. They'll be about 1 to 2 millimeters thick. We found that if we had films much thinner than that, they tended to pop when the soldering iron was inserted. And we're going to try to keep the geometry simple. We're going to try to keep the barrel of the soldering iron held perpendicular to the film so that you've got a nice cylindrical geometry to the system. And let's go ahead and see what happens. Here's our edge-on view of the film. Again, it's about 2 millimeters thick, and the tip of the soldering iron is penetrating the film. And eventually we'll just go ahead and poke the soldering iron in far enough so we have the nice cylindrical barrel of the soldering iron immersed in the film instead of this tapered cone.
Here's a slow motion of the tip penetrating the film, and you can see that surface tension forces through contact wetting angle distort the shape of the film and pull it up onto the barrel of the soldering iron.
Here we see another view of the soldering iron going into the film, and it drives convection right away. The convection gets started. You see these closed circular loops with little bubbles forming, and the heat from the soldering iron, possibly Marangoni convection, is causing the fluid to circulate around, and it's whisking the bubbles off of the surface of the soldering iron, allowing new, fresh fluid to be heated next to the wall. And here's another view of the soldering iron. Again, the barrel has been inserted all the way into the fluid, and it's being held perpendicular to the film.
And the diameter of that barrel is about 8.5 millimeters, and the whole diameter of the film is 50 millimeters, and the thickness of these films ranged in the 2 to 3 millimeter thickness.
And you can see that bubbles are forming at the surface. They expand. This expansion process drives the water away into these convection cells, and the convection cell in turn helps take the bubbles away from the wall, allowing cooler water to go back in contact with the wall, and it's just driving the whole process in this a circular manner.
Now, when you devise a series of observations like this, you like to keep the geometry simple so that you can describe what's going to happen with easier mathematical equations. And with the tip of the soldering iron leaning over like this in the water, it makes rather difficult geometry to analyze.
And these experiments were done in our little maintenance work area glove box. It looks like a little plastic tent, kind of like a terrarium with glove ports. And you can do soldering operations and other maintenance activities inside of this glove box. And we chose to do the boiling experiments inside of the glove box so we wouldn't have to worry about little droplets of hot water floating around in our wet chemistry lab. Here we see one more example of boiling, where we squirt a spherical blob of water onto the barrel of the soldering iron, and we just watch it in sequence here as it reaches a full rolling boil. And I found this amazing in that the bubbles form on the surface, they break away from the surface, and then they continue to circulate around. At the first order, this boiling in a weightless environment doesn't look that much different than boiling that you see on the bottom of a pot on the stove in your kitchen back home.
And there, gravitational-driven buoyancy supposedly is what removes the bubbles from the heated surface, and the buoyancy-driven convection driven by gravity keeps things stirred around. But here we do not have any of those forces available, and other forces spring forth and take the place and cause convection to occur in a manner that's not that much different than what you would see on the ground.
That was the amazing thing to me, because I thought that you would see water vapor form on the heated surface and just stay there, and then eventually exclude the surface from having a contact with water. But that didn't happen. The bubbles form on the heated surface, they pop off through a variety of mechanisms. More water can reach the surface, then get heated a second time, and you just get this boiling process that's going that the first order looks just like what you see in your kitchen pot.
You like to keep the geometry simple so that you can describe what's going to happen with easier mathematical equations.
This boiling in a weightless environment doesn't look that much different than boiling that you see on the bottom of a pot on the stove in your kitchen back home.
And Houston Alpha, that's it for our Saturday morning science.